Every morning, millions of people around the world reach for a razor blade without giving much thought to the intricate manufacturing process behind this everyday grooming tool. The creation of a modern razor blade is a fascinating blend of metallurgy, precision engineering, and quality control that transforms raw steel into one of the sharpest edges commercially available. Let's dive deep into the remarkable journey of how razor blades are made. The raw material. The process begins with the selection of high-quality steel, typically a specialized stainless steel alloy. Manufacturers favor stainless steel because it resists corrosion from water and shaving creams while maintaining exceptional sharpness. The steel used in razor blades contains chromium, carbon, and other elements carefully balanced to create the ideal combination of hardness, flexibility, and edge retention. The steel arrives at the factory in large coils, each weighing several tons. These coils have already been processed to achieve the precise thickness required for razor blades, usually between 0.1 and 0.4 millimeters. This ultra-thin material must be perfectly uniform because even microscopic variations could affect the blade's performance. Cutting and shaping. The manufacturing process truly begins when the steel coil enters the stamping machine. High-speed presses punch out blade blanks at remarkable speeds, often producing thousands of pieces per minute. These blanks are the rough outline of the final blade, complete with holes for mounting and the basic shape that will eventually hold the cutting edge. The stamping process generates significant heat and stress in the metal, so the blanks must undergo annealing, a heat treatment process that relieves internal stresses and softens the steel slightly. This step is crucial because it prepares the metal for subsequent hardening processes and ensures consistent blade performance. After stamping, the blade blanks enter a carefully controlled heat treatment process. They're heated to temperatures between 1,000 and 1,100 degrees Celsius in specialized furnaces with precisely regulated atmospheres. This prevents oxidation and ensures uniform heating throughout each blade. The heated blanks are then rapidly cooled, or quenched, in a controlled environment. This quenching process transforms the steel's molecular structure, dramatically increasing its hardness. The result is a blade blank that's incredibly hard but also somewhat brittle, which brings us to the next critical step: tempering. Tempering involves reheating the hardened blades to a lower temperature, typically between 150 and 300 degrees Celsius. This process reduces brittleness while maintaining most of the hardness gained during quenching. The precise tempering temperature is a closely guarded secret for many manufacturers, as it significantly influences the blade's final characteristics. Modern razor blades rarely remain bare steel. Manufacturers apply various coatings to enhance performance, durability, and comfort. The most common coating is chromium, which provides excellent corrosion resistance and a smooth surface that glides easily across skin. Some premium blades receive multiple layers of different materials. Platinum chromium coatings are popular for high-end razors, offering superior durability and an exceptionally smooth shave. Polymer coatings may also be applied to reduce friction and enhance comfort. The coating process typically involves physical vapor deposition or electroplating. In physical vapor deposition, the coating material is vaporized in a vacuum chamber and then condenses onto the blade surfaces, creating an incredibly thin but uniform layer. This high-tech process ensures every microscopic portion of the blade receives consistent coating coverage. If you're fascinated by the precision engineering behind everyday objects, subscribe to our channel for more in-depth looks at manufacturing processes that shape our daily lives. Creating the razor-sharp edge is perhaps the most critical and challenging aspect of blade manufacturing. The sharpening process involves grinding the blade at a precise angle, typically between 20 and 30 degrees, though exact angles vary by manufacturer and blade design. High-speed grinding wheels made from industrial diamonds or other ultra-hard materials remove material from the blade edge with microscopic precision. The grinding process occurs in multiple stages, each using progressively finer abrasives. The first pass removes bulk material and establishes the basic edge geometry. Subsequent passes refine the edge, removing scratches and imperfections left by previous grinding stages. The final sharpening stage, called stropping or honing, creates an edge so fine that it approaches the theoretical sharpness limit for the steel. Modern razor blades achieve edge radii as small as 100 nanometers. That's about 1,000th the width of a human hair. At this scale, the edge is actually sharper than many surgical scalpels. Throughout the sharpening process, cooling is essential. The friction from grinding generates tremendous heat that could ruin the blade's carefully controlled hardness. Manufacturers use specialized cooling fluids and precisely timed grinding cycles to maintain optimal temperatures. Given that even microscopic defects can compromise a blade's performance, quality control is paramount. Modern razor blade factories employ sophisticated testing equipment that examines each blade with incredible precision. Automated optical inspection systems scan every blade, looking for chips, cracks, or irregularities in the edge. Laser measurement systems verify edge geometry and coating thickness. Some manufacturers test blade sharpness by measuring the force required to cut through standardized materials like special test papers or synthetic skin analogs. Statistical sampling tests evaluate blade performance under real-world conditions. Select blades from each production batch undergo actual shaving tests using specially designed equipment that simulates human skin and hair. These tests measure cutting efficiency, durability, and comfort characteristics. Any blade that fails to meet stringent quality standards is immediately rejected. For premium brands, rejection rates can be surprisingly high, sometimes exceeding 5% of production. This uncompromising approach to quality ensures that only blades meeting exact specifications reach consumers. Assembly. For cartridge razors, individual blades must be precisely assembled into plastic housings. Automated assembly lines position multiple blades at specific angles and distances, often with microgrooves or lubricating strips positioned between them. The spacing between blades in multi-blade cartridges is critical. If blades are too close together, they'll clog with hair and shaving cream. Too far apart, and they won't deliver the close shave consumers expect. Manufacturers measure these distances in micrometers and maintain tolerances that would impress aerospace engineers. Lubricating strips, moisture-activated substances that provide glide and comfort, are attached during assembly. Some cartridges also incorporate pivoting mechanisms, trimmer blades, or other features that add complexity to the assembly process. Finally, completed blades or cartridges are packaged in protective containers that prevent damage and corrosion during shipping and storage. Many manufacturers use inert gas environments or moisture-absorbing packets inside packaging to extend shelf life. The entire journey from steel coil to packaged razor blade typically takes several days, with each blade passing through dozens of individual processing steps. The result of this complex manufacturing process is a product so sharp and precisely made that it can comfortably remove hair at skin level, shave after shave. Modern razor blade manufacturing continues to evolve. Researchers explore new steel alloys, advanced coatings, and innovative blade geometries. Some manufacturers experiment with laser sharpening techniques or nano-structured edges that promise even better performance. The humble razor blade represents a triumph of modern manufacturing, a commodity product that nonetheless demands cutting-edge technology and uncompromising quality control. Next time you shave, take a moment to appreciate the remarkable engineering and precision that went into creating that incredibly sharp edge. Want to explore more amazing manufacturing processes? Subscribe now and join us as we uncover the hidden complexity behind everyday products that we often take for granted.